Hey, ZSauce, Zoraise here. But what is here? Humans by nature are social creatures. We like to meet up with each other, to hang out, and to share stories. When you call a friend and say, "I'm here," are you really? The Earth is constantly rotating at around 1,600 kilometers per hour. We're also orbiting the Sun at about 108,000 kilometers per hour. Our galaxy is also moving through the universe at around 2.1 million kilometers per hour. So just remember that the next time you tell your friend, "I'm here," you've already moved thousands of kilometers throughout the universe since the moment you said, "I'm here." Now, the movement of the Earth can be explained by Newton's first law, which states that any object that's already in motion will remain in motion unless acted upon by an external or imbalanced force. Wait, this isn't right? Newton's second law states that force equals mass times acceleration. Newton's third law states that any action must have an equal and opposite reaction. Now, Newton's three laws typically work how they're supposed to, like laws. The universe abides by them and everything works out. They're the reasons why we have rocket launches, why we can crash test cars to make sure they're safe, and a whole host of other things. But once you go small, to the quantum scale, things start to get weird. Newton's laws just don't work anymore. And this book right here, The Quantum Universe by Brian Cox and Jeff Forshaw, tries to explain what happens when we go very small. Now I'm going to say a few things that might sound a little bit weird. This is quantum mechanics, and quantum mechanics are weird. So we'll start with this. On page 46, the authors say that a particle can be anywhere in the universe at one instant, and it could be anywhere else in another. In 1 second, a particle could be right here above my finger, and in another, it could be all the way out at Saturn. This might sound a little bit weird if you're familiar with the theory of relativity. Any object cannot be moving faster than the speed of light. So how can a particle get from here all the way to Saturn in an instant? And the answer is that because there is no information being transmitted, it's just a particle. It can do that. It doesn't break Einstein's laws. Now, if you're confused at this point, don't worry, because a lot of physicists are. In this book, it's later stated that Richard Feynman, a famous American physicist, once said, "I think I can safely say that no one understands quantum mechanics." One of the reasons why we have such a hard time understanding quantum mechanics is because we try to draw comparisons to things. Humans look for patterns. If something happens in nature, it must happen for subatomic particles. But that isn't the case. This book talks about the Heisenberg approach, which is a method of thinking that involves forgetting everything you know and stopping to look for the logic in things, because nature is illogical. Now, if you're interested in this, be sure to give this book a read. It starts from the early days of quantum mechanics from Niels Bohr all the way to the present day, with current and modern day experiments happening. I hope you guys learned a little bit about the world that's small. And as always, thanks for watching.